So last topic, I want to show you guys volume by slicing. So here's how this works. The whole point of volume by slicing, this is useful when the cross-sectional area of some volume is a function of x or y. Okay, and then so you're able to link. And it helps to see a picture. I'll come back to this, but like here's an example of a picture where that would be true. Now this is a volume in this example that we could have done by the disk method or the shell method, but it also works to use slicing, because if we have this cone that's oriented the way it is on here, you can see that as we move along from 0 out to the end of this cone, the value of x predicts the size of the cross-sectional circles. So I can set up an integral to sum up all of those cross-sectional areas as a function of x. Okay, now this is an example where we could have used other methods, but there are other types of examples like this one where we couldn't, where there is no rotational symmetry, and this is where slicing is particularly useful. Okay, so again, let's head back. So again, idea is we're going to be cutting these thin cross-sectional slices perpendicular to an axis, and then we're going to add up all the volumes of those slices just using integration. Underlined here, you can see slicing relies on the fact that the area of each cross-section obtained by slicing can be expressed as a function of the position of the slice. Frequently, there is no, like the problem is just kind of abstract, and it's not necessarily embedded in any kind of a coordinate axis or anything like that, or in a coordinate plane or in a volume. And you have the freedom to orient the coordinate axes in the most convenient way just to sum up the volume. And usually there's a way that makes sense to do that. So here's kind of the formula is pretty simple. The volume, if we're slicing perpendicular to the x-axis, it would just look like this. The volume is just going to be the integral of a of x dx, where a of x is that predictable cross-sectional area as a function of x. So let's just look at a couple examples. What about one like this? So let's use slicing to verify the formula for the volume of a right circular cone with radius r and height h. So we're going to orient the cone in the most convenient way. So we're going to stick the cone where the vertex is right at the origin, and it's just going to open up with the axis of symmetry being the x-axis. Okay, what would the cross-sectional area of one of those circular slices be as a function of x then? How are we going to get that? There you go, right? So if we can just have, and we can do that with the equation of the line would be a convenient way to do it. Exactly analogous to that would be something like just using a ratio of similar triangles, something like that. Does it make sense that something like that predicts the area of the circle, right? If I'm going to proceed along by it, and what are they doing here? What are they doing here? How are they coming up with that? Well, they're just using these similar triangles, aren't they? Right? For any given value of x, the radius small r is going to be related by this relationship, because we know the height of the cone is a constant, and the capital R radius of the base of the cone is a constant, right? So those aren't changing. Then we can just set up this ratio x over r. Actually, we want to do it the other way, don't we? Not that it makes a huge difference. Let's do this. r over x equals capital R over h, right? And so if I solve for r as a function of x, it just equals rx over h, right? And we know that the area of a circle is just pi r squared, so there it is. There's r of x squared, right? Okay, makes sense? And we're just going to integrate that. We're just going to add those slices up as x goes from 0 up to the end of the cone, which is at h, at the height of the cone. Okay? That's the cross-sectional area, the thickness of each. What's the thickness of each slice? dx, right. So then there's our integral. That's a pretty easy integral to do because, again, capital R and H are constants. We just pull those in pi. We just pull those out in front of the integral, and we've got a pretty trivial integral to do then. Right? So we just end up with, with the correct volume for, formula for a right circular cone then. Okay? Does that make sense how we did that? Really, these are not hard problems. It's just about orienting the shape correctly so you're able to easily link the cross-sectional areas to a value of the input variable. So what about one like this then? So a solid has a circular base of radius 3. And I always kind of think about these, like I call these coffee table problems. Like imagine that you're setting these down on a glass coffee table. Then if you're underneath looking up at the base of the at the coffee table from lying underneath the coffee table, you're seeing that base, right? All we know is that has a circular base of radius 3, and we know that every plane cross-section that is perpendicular to a fixed diameter is an equilateral triangle. Okay, now think what that means. Every plane cross-section, that just means slice, that's perpendicular to a fixed diameter. Well, a diameter is just going to be a line that travels, through the center of the circle, right? So we're going to be, a fixed diameter means that's going to be constant, and we're just going to make slices perpendicular to that line that forms the diameter. If all of those slices are defined to be equilateral triangles, then that's the picture we get, isn't it? Right? And you don't even really have to be able to visualize what the three-dimensional picture is like if you're in a hurry. That maybe isn't even worth wasting time thinking about that. If you just know what the cross-sections look like and you know what the limits of integration are, you can just do the integral, right? So we've got to come up with, really the tricky part is just finding how do we link the area of the cross-sections to the value of x in this case. And pretty clearly we want the x-axis. We're going to be slicing perpendicular to x, so the x-axis has to form that extended diameter, right? The x-axis has to travel through the diameter. Give me thumbs, does that make sense? Okay, there's some symmetry here too. What would my limits of integration be in this case? Do I have to go all the way from -3 to +3? What could I do? Just double it, right? There's symmetry there, so you're just going to go 0 to 3 and double it. Okay, so then this ends up, and there's the value of y, right? And notice that y in this case, that this thing is sitting on the xy plane, right? So y is forming the height as seen when you're lying under the coffee table staring up. Y represents half of the base of this triangle then, doesn't it? Right, as this is oriented. So how are we going to come up with the area of this triangle? Like that, right? Does that make sense? So the x-axis is running perpendicular here. Here's the y-axis. And whether you want to call it y, or you don't even have to call it y if you don't want to, but the base then is going to be 2y, and it's equilateral, so each of the diagonals is 2y, which makes it really easy for us to calculate h, right? Look, you've got this right triangle here with a height h. If I just look at this right triangle, this one little tiny right triangle down here, and I'm looking at just this guy, we want a right triangle so we can use Pythagorean theorem, then it's easy for us to solve for h in terms of, just in terms of y, right? And so we end up with h equals, h squared equals, h squared plus y squared equals the quantity 2y squared, so 4y squared. Solve for h, you just get h equals square root of 3y. Okay? And so the area of the cross-sectional triangle is just going to be half the base, which is y times h. Easy.
How did you figure out that hypotenuse was 2y?
I'm sorry?
How did you figure out the hypotenuse was 2y?
Because it's equilateral, right? So if that's y, so the base is 2y, it's equilateral, so all the sides are 2y. Okay? What am I doing here? Where's that? There we go. Oh, I see. It's taking that too. All right. Okay, makes sense? And so that's what our picture looks like then, right? There's an individual slice. Okay? And so the area then of an individual slice is just going to be, like we said, half the base, which is 2y, so that's just y times the height, which is square root of 3y, square root of 3y squared. We want to write this in terms of x's though, right? We want this as a function of x. That's easy to do because look at the relationship between x and y. This is a circle, right? And there's the definition. Okay, they tell us that the base is a circle of radius 3. Well, what's the equation of a circle centered on the origin of radius 3? That's just x squared plus y squared equals 3 squared, right? And so y equals 9 minus x squared. Y squared equals 9 minus x squared. Conveniently, we've got a y squared there. We don't even have a y. We have a y squared. So we just trade that for a 9 minus x squared. And there's the area of our slice as a function of x. Whoops. So the volume of a slice is just that times the thickness dx. And we just sum that up with an integral. And that's no big deal. That's an integral we can easily do. And we'll take advantage. We'll take advantage of the fact that we've got symmetry, and we'll just go from 0 to 3 and double it. Okay? Does that make sense? Good with that? Okay. Okay, how about something like this? So a region R in the xy plane is bounded by the graphs of y equals the square root of x and y equals 1/8 x squared. So there's a picture, right? We're looking for the bounded region. There's the region enclosed. Find the volume V of a solid whose base is R if slices perpendicular to the x-axis have cross-sections that are squares. So we're going to be making our slices look like this. Like here's a slice, for example. When I make that slice, the cross-section is going to be square. So if it came out of the paper, it would kind of look something like that. Does that make sense? Okay. Okay. So what's the cross-sectional area going to be then? All we really need to know is that distance, right? The distance between the two curves, and that's the side of a square. So I square that distance to get the area, right? There's my top curve, there's my bottom curve. Right? There's a better picture. Okay. So I guess with this one we just are going to do. when we're all done with this, I have an interesting question for you. So what's our integral going to look like then? Yeah, so we got our volume equals the integral. We need the cross-sectional area as a function of x. So what's the cross-sectional area is just going to be the side length of a square squared dx. What's that going to look like? Yeah. Blue curve minus whatever that is, pink curve, right? So square root of x minus 1/8 x squared dx. From where to where? Yeah, okay. And we don't even need to do that one, right? I mean, that's one we can all do. If we just square this out, we're just going to get a trinomial, right? It's not really a trinomial. We're going to get 3 terms, and each of those is going to be a power of x. Just integrate that term by term, and we got it. The main part is just being able to set it up. I got a question for you. Does it have to look like that? That's the way it's been described. But would this thing have to sit in a plane? Could it have could it look like how would I describe this? Could it look kind of like a torpedo where it's got symmetry along an axis? See what I'm saying? Could I kind of smush it down so it looked like in cross section, instead of looking like right now, if I were to look at this in cross section, if I were to look at this edge right here, it looks like that. Everybody agree? And then if each of the pieces that form that are squares in cross section. Could I instead make it look like this and have this and preserve the volume? Could it instead go like that, as long as the edges are the same width? Could I reconfigure that without changing the volume? Do you see what I'm getting at? I didn't describe that very well. You see what I'm getting at? Could I? Does this really have to be a coffee table problem, I guess is what I'm saying? Do you have to be able to set this on a coffee table and have a flat base? This surface is curved, that surface is curved, the back surface is curved, but the bottom is flat. Could I do the same? Could I make all the surfaces curved? What do you think?
So if you want to do that, would you place the squares their midpoint?
That's a good way to describe it. Yeah, the center of the squares would be on the x-axis then, exactly. Would that change the volume? You're saying no, you're saying yes. It's a good argument here. It looks like it might, right? But the integral is going to tell the tale. Is it going to change the integral? Because if it doesn't change the integral, it doesn't change the volume. See what I'm saying? So that's kind of as I was putting this thing together, I was just thinking about that. That kind of gives you a little insight into when you're creating these higher dimensional shapes. And you could apply this to dimensions higher than 3 then too, mathematically, right? But for us, it'd be easy to visualize with 3. That's really the tail of the tape there. I mean, if you can set up an integral that sums this up, and any kind of morphing you do of the shape, right? Any transfiguration, as long as it doesn't impact the structure of the integral, It's not going to change the volume, right? And that's kind of a principle. If you went way, way down the line, like if you look at topological math, that's the kind of thinking they do in topological math a lot of times, where they're looking at changing topologies. Like this kind of a bizarre thing. I might have even said this one to you guys before, but like if I set up 3 objects, say I have a glass, a mug, a coffee mug, and like one of those, those Frisbee things with a hole in the middle, those aerobies that are real flat that just go forever. You know what I'm talking about? They're kind of heavier, but they really fly. Which of those 2 things are most similar topologically? I mean, you're tempted to say that the cup and the glass, obviously, right? Because they both contain liquids, but it's not. It's the mug and the aerobie, or we could make it a hula hoop instead. So that's somewhere, because they each have one closed loop. And when you do the math in topology, what's equivalent to what we're talking about here, like one of the metrics that they would track would be the number of closed loops in an object. And it's easier to, how do I say it? So you could smoothly reconfigure a hula hoop if it's made out of clay to turn that into a mug without ever breaking that one loop. But the glass doesn't have a closed loop. There's no way to move from a glass to a mug or a hula hoop, because you'd have to introduce a closed loop that wasn't already there, right? And so the 2 kind of remind me of each other just a little bit. What about part B? What if we wanted to slice perpendicular to the y-axis, having cross-sections that are squares? Now that's going to be a different animal, isn't it? Right? See what that's going to look like. It's going to, if we're slicing perpendicular to the y-axis, and this is defined as our base, then then these are the slices, and those are defined to be squares, right? It's going to look a little bizarre. It's going to be kind of like shifted a little bit, so it's, I don't have a picture of it, but you can probably evoke an image. Not super hard to do, though, because the integral now, all we're doing is we're just substituting an integral with where the thicknesses are dx for one where the thicknesses are dy, and now the quote-unquote height of that, or the length of the side of the square, is just going to be pink minus blue as functions of y, right? Not a big deal. I would just have to rewrite this down here. I would just have to rewrite that guy solving for x. Now if I solve for x, I'm going to end up getting, what do I get if I do that? I get x squared equals 8y, so x equals plus or minus the square root of 8y. Well, we're only going to take the plus one, aren't we? Right? We're just going to take the positive trajectory of that. And then this guy's pretty easy. This guy up here, if I solve for x, I just get x equals y squared. So it's a reasonably simple integral then for part B. We're just going to get volume equals the integral of pink minus blue squared, right, dy from where to where? 0 to 2. Yeah, right? That's no big deal. And again, we're just going to, if we just expand out that binomial, we're just going to get powers of y. They're going to be fractional powers, but big deal. That's easy to do. Those are no big deal. Okay? Find the volume h of a pyramid of height h with a square base, each side of length b. Okay? So that's what we're looking at, right? Again, does it matter? In this case, the x-axis goes right through the center of each square. What if I reconfigured this so the x-axis formed like either the altitude of one of the triangles on the side, or what if it's even one of the edges, right? So this could be a pretty bizarre looking pyramid if I did that. So like this is an edge, and it's going to go is it four-sided? Yeah. Oh, that's pretty bad. I get that. You get the idea. You get the idea, though. So one edge would be a lot shorter than a couple other edges, right? Is that going to impact? Geez, that's bad. That's going to impact. That's like one of those impossible shapes. It's going to impact the surface area, obviously, isn't it? Right? If we reconfigure it like that, you're gonna change the surface area when you transfigure that volume. But is it going to affect the volume? No, right? Because the cross-sectional areas are still going to be the same, right? They're still going to be defined as having the same side length in their squares, and the limits of integration stay the same, right? But remember, we're adding up volumes, we're not adding up surface areas. So just because volume's preserved doesn't mean surface area is, right? And that's easy to see. Like if I take a volume of material and I flatten it out into a puddle, obviously the surface area rises massively, but the volume stays the same. Okay, so then what's the cross-sectional area going to be if we want to set up this integral? What's a of x going to be? Gotta use a ratio, don't we? Yeah, gotta use a ratio. So it's gonna be, what do we got here? They probably got a much better picture than I do. Yeah, there's our ratio, right? So side length, if I go over some distance x, the side length is going to be in proportion to the total height and the total base, right? We got these similar triangles. And so, yeah, we just end up getting, there's our cross-sectional area. There's what we end up getting, right, using that ratio. Side length is going to be some function of x dictated by whatever the ratio of b and h is, b to h. Okay? Make sense? And I hate to get rid of my beautiful drawing down there. I don't even know what that's there for. So if that's the volume of one section, we're just going to sum up that integral. Everything's a constant there except x, so that's a super easy integral, right? We just end up with this. B and H are constant, so those can go out front. And our limits of integration would be from what to what? 0 to h, yep. Okay. And so what's that going to give us? B squared over h squared. Integral of x squared is what? X cubed over 3. Evaluated from 0 to h. Well, that's just going to give us b squared over h squared times h cubed over 3. So b squared at 1/3 b squared h. Okay. Isn't that what you would predict, though? Isn't that, I mean, if I asked you to make a prediction, that's probably what you're going to predict, because the volume of a right circular cone is 1/3 pi r squared h, right? It's just 1/3 of the corresponding volume of a cylinder, right? So shouldn't this be 1/3 of the corresponding volume of a right prism, rectangular prism, right? Kind of cool that there's that symmetry there. All right, I think you got it. It's not a big deal. I don't know if we'll do anything else. That's probably good.